So then, what are we going to do today? Today we're going to do something that's a little bit less exciting, but nonetheless is a kind of important part of the chemistry which we need you to be able to do. And indeed, if you go on and do chemistry in all sorts of different areas, buffers are something that you're going to come across. It's very important in biochemistry, very important in a lot of environmental chemistry, and a lot of the time, if you don't know the chemistry, then you're kind of just reliant on using the recipes that you get out of books, or dare I say it, online, to make up your buffer solutions. Whereas if you actually understand how buffers work and sort of the underlying chemistry, then you can be free of being stuck to recipes and you can make your own buffers and you're a lot better off for doing what you've got to do. And they're not that hard, it's just there's another formula we have to learn and just a little bit to understand. So, buffer solutions today. And this kind of builds on what we were talking about in the lab yesterday a little bit. At the end of yesterday's lecture, we saw this titration curve, which is the titration curve that you get when you have a weak acid in your little flask and you have a strong base in your burette. And so you did this in the lab yesterday. You titrated sodium hydroxide, that was in the burette, with ethanoic acid or acetic acid. Sorry, there's still some confusion there. I'm going to be good today. I'm going to say ethanoic acid, except for when I forget, because that's what's on the slides. They're two different names of the same thing. Yeah. So you've got ethanoic acid, which is a weak acid, in the little flask underneath your burette. And so if you slowly add the sodium hydroxide to that, and you measure the pH, and you did this yesterday, I think, in the lab, then you get a curve that looks something like this, where initially the pH goes up quite quickly, and then it seems to flatten out for quite a while, and then the pH goes up again very quickly, and then finally tails over at the end. So this very characteristic shape that you get for a weak acid being titrated with a strong base. And so yesterday we talked about how you know enough chemistry now to be able to calculate the pH before the retitration starts, so calculate the pH of just the solution of the weak acid. We went through yesterday how you go about doing that calculation. You also now know how to calculate the pH at the very end of the titration, because at the very end, then all you've really got is just a solution of sodium hydroxide. If you keep adding and adding and adding and adding hydroxide, eventually it's just slightly diluted hydroxide solution. You know how to calculate the pH of that, hopefully, from what we did yesterday. What we want to do today is look at this little bit where the pH flattens out on the way to the equivalence point. I think we're also going to look at the equivalence point a little bit, but mostly we're going to be focused on this flat region, which is called the buffer region. Lyndon yesterday asked me whether there was a name for the thing in the middle called the buffer point. Some people call it the buffer point. I don't think that's actually a thing that's in textbooks. I think people just make that up. But this flat region in general is called the buffer region. Right? So we're going to be looking at points B and C and D in this curve today. And to understand what's going on, we need to think about what is in the solution at point C. Remember I said yesterday, I'm all about trying to understand what's going on in the little flask. So we want to think about what's going on in the little flask at point C, which if you look at the x-axis closely, you'll see is halfway to the equivalence point. Okay? So here's a chemical equation that describes the reaction that happens when we add our sodium hydroxide to our ethanoic acid. Right? So the CH3COOH reacts with the OH minus. It's a one-way arrow because even though ethanoic acid is a weak acid, and so it doesn't really want to give away its proton very much, hydroxide is a strong base. And so ethanoic acid doesn't want to give away its proton, but the hydroxide doesn't care. It just comes and takes it because it's a strong base. That's what they do. Yeah? So this is not a reaction, this is not an equilibrium reaction, this is a reaction that goes to completion. So the CH3COOH reacts with hydroxide ions to give ethanoate, CH3COO-, and water. Okay, and so to recap our words from yesterday, CH3COO- will be the conjugate base of the ethanoic acid, H2O will be the conjugate acid of OH-. Yeah? As we add the hydroxide from the burette into the little flask that contains our ethanoic acid, the hydroxide immediately reacts with the ethanoic acid and turns into water. Right? So as soon as you add the hydroxide ions, they immediately go and find themselves an ethanoic acid molecule, pull its proton off, and turn themselves into water. And so what you're left with, a very short time after you've added each drop of hydroxide, is you're just left with water and ethanoate ions, the products of that reaction. Yeah? And so as we add the hydroxide, the ethanoic acid is slowly changed into its conjugate base, into the ethanoate. So you add the hydroxide immediately reacts and turns into water, and the acid gets converted into ethanoate. And so the point to make here is that we consider that the solution contains no hydroxide ions at this point in the titration. Because as soon as you add them, they react and turn into water. Now, of course, this isn't 100% true, because as we saw yesterday, there's always going on in the background in a reaction that you have in water, this two waters reacting with each other to make H3O plus and OH minus. So there's always going to be a little tiny bit of OH minus in there. But it's going to be such a small amount in the situation that we can neglect it. We don't have to worry about it. Okay? There'll be a tiny, tiny amount, but very, very little. Okay. So whilst at point A, good Lord, whilst at point A the solution contains only ethanoic acid, as we move to points B and C and D, the solution contains progressively less ethanoic acid and more ethanoate. Okay? So as we're adding our hydroxide and we're beetling our way along our curve like this, then as we go, the amount of ethanoic acid in our flask is getting less and less and less, and the amount of ethanoate is getting more and more and more. Okay? And we kind of said this yesterday in the labs, because you had to, on your curve, you had to break up that region into the region where there was more ethanoic acid than ethanoate, and where there was more ethanoate than ethanoic acid, yeah? So this is the same thing. And so what we can see from the curve is that if you initially have ethanoic acid in your flask and you start adding hydroxide to it, and the ethanoic acid turns into ethanoate, then the pH starts going up, which is what you would expect, because you're getting less acid in your solution. But then, once you start getting a reasonable amount of ethanoate present in the flask as well, the product of the reaction, then the pH stops changing so rapidly. Right? And so we get to this buffer region. And so what we can say is that if the solution contains appreciable amounts of both the ethanoic acid and the ethanoate, both the weak acid and its conjugate base, then the pH doesn't change very much as we keep adding hydroxide. Eventually we add enough hydroxide that suddenly it does start changing again very quickly. But for a while, we keep adding hydroxide, but the pH doesn't seem to change very much. But we only have that when we get far enough through the titration that we've got a significant amount of the conjugate base there, which has been generated as a product of the reaction itself. Does that make sense? Yeah? And so this then leads us to our definition of a buffer. It's a definition that's in two parts, and you need to know both parts. One part tells you about what a buffer is, and the other part tells you what a buffer does. Okay, so we define a buffer like this. A buffer solution is one which contains similar amounts of a weak acid and its conjugate base, or, if you like, a weak base and its conjugate acid, which is able to resist changes in pH when small amounts of strong acid or strong base are added to it. Okay, so a buffer is one which is a solution which contains similar amounts of a weak acid and its conjugate base, or a weak base and its conjugate acid. So that's the part that tells you what a buffer is. And then the second part tells you what a buffer does. It's a solution which is able to resist changes in pH when small amounts of strong acid or strong base are added to it. This is exactly the sort of thing that that's important enough that I'm likely to put it in the assessment on Friday. Yeah? And it'll be in the lab. The lab today is on buffers. It could well be in the exit test as well. I don't know. But you need to know this, yeah? Okay. So how does it work? Well, and often we ask this too. This is often an exam question. The pH change in the solution is minimized because when strong acid is added to our buffer solution, it reacts with the conjugate base in the buffer solution, right? So the thing to remember is that acids react with bases, and bases react with acids. So if you have a buffer solution that contains a weak acid and its conjugate base, and you add some strong acid to it, the strong acid that you add will react with the conjugate base part of the buffer, right? So if your buffer is a solution of ethanoic acid and ethanoate ions, like in our titration that we've been talking about, then if you add strong acid, and here's the strong acid, and this could be hydrochloric acid, but remember hydrochloric acid immediately reacts with the water to make H3O+, because it's a strong acid, that's what they do. So H3O+ then will react with this, the base part of our buffer. This will transfer its proton from here onto here, and you're going to make some ethanoic acid, and you're going to make water. Right? This is a one-way arrow because this is a strong acid. This doesn't necessarily want to get the proton, but this doesn't care. It'll just shove it on it. Right? So this will become ethanoic acid, this becomes water. Right? So if you like, this thing here is very good at giving away its proton. It's a strong acid. But what happens is that this proton, which when it's here, is very readily able to be added to something to do the acid-base chemistry, it gets transferred to this where it's a lot better tied up, right? So once the H plus is on here, it doesn't come off nearly so readily. So it's a bit like, I've been trying, for a long time, trying to come up with a good analogy of this, but it's a bit like if my text was actually real and I have just won €1 million, yeah? Yeah. If I had €1 million in cash in my hand, then that would be very easy to spend. Well, actually it wouldn't, because it's a lot of money. But in theory, it would be very easy to spend. If I was a good boy and I took my €1 million and I took it to the bank, then it becomes much harder to spend because I have to go to the bank and I have to get the money back out. Or I at least have to go to a machine and get the money out, right? So if you've got cash in your hand, it's very easy to spend, but if it's in the bank, then it's much harder to spend because you have to go to the trouble of getting it, yeah? This is kind of the same thing. Here, with the H plus on this molecule is very readily able to be used to protonate some other molecule, because this is very happy to get rid of it, and so this is a very good acid. Here, the H plus is a lot harder to use because it's much more tied up in this molecule. Does my analogy work? Do you kind of see what I'm getting at? Yeah? I see a sea of unconvinced faces. If we add strong base to our buffer solution, then it's the same deal. The strong base, the hydroxide ions, will react with the acid part of our buffer, the ethanoic acid, and so the reaction will be this. OH minus reacts with CH3COOH to give CH3COO minus a weak base and water. So what in effect we're doing is if we add strong acid or strong base, see, I can't think of the right word for this. The acidness of the acid is reduced, or the basicness of the base is reduced because you're changing it from being in the form of a strong acid to being a weak acid, or a strong base to being a weak base. And so what this does is it minimizes how much the pH changes, because the pH, remember, is a measure of how much H3O plus there is in the solution. And so if we do this, then this H3O plus, which is an acid, gets turned into acetic acid, which is also an acid, but is much less good a source of H3O plus, because only a small amount of the ethanoic acid actually dissociates to give H3O plus. Is this making any sense at all? Yeah? We'll press on, maybe it will all become clear. Maybe in the tutorial they might say it a different way and you go, ah. This is quite hard. I find this bit quite hard to explain. But it is important that you know the equations, right? If nothing else, as we're going to see in the problems that we're going to do, the first thing you have to do, like in yesterday with our step 1, write the equation. For these will be step 1, write the equation. And so you need to know that if you have a buffer solution and you add a strong acid to it, then you want to write an equation like at the top there. The strong acid reacts with the conjugate base part of your buffer. If you add a strong base, it reacts with the weak acid part of your buffer. Yeah? You need to know that bit in order to be able to then do the calculations. Okay, shut up, move on. The other thing that we did yesterday when we were talking about weak acids and weak bases was we saw that because those are equilibrium things, the weak acid reacts with water in an equilibrium reaction, then we can write equilibrium constants for those reactions. And so now we're taking a step back. This isn't the reaction we're just talking about. Now this is just ethanoic acid reacting with water to give ethanoate and H3O+. And we saw that the equilibrium constant expression for this reaction looks like this. The Ka is the concentration of ethanoate at equilibrium times the concentration of H3O+ at equilibrium divided by the concentration of the ethanoic acid that doesn't react at equilibrium. And so yesterday we saw how if we've got a solution just of a weak acid, then we can work out the pH of that solution of a weak acid using this expression, using the assumptions that we saw that you can make, and so solving that expression for concentration of H3O+. Right? That is for when you have a solution of just a weak acid. What we can do with this equation, using math that I'm not going to go through, is we can rearrange this and we can do some logging to it and we can fiddle around and we can transform it into something that looks like this. This is something called the Henderson-Hasselbalch equation. You don't need to know the name necessarily, but you need to know the equation. This is the equation that you use for working out the pH of a buffer. Right? This is the equation that you use for working out the pH of a buffer. Stop writing for a second. Repeat after me. This is the equation we use for working out the pH of a buffer. Because I will guarantee that we'll go to the tutorial and half of you will try and use this for working out the pH of a weak acid. This only applies if you have a solution which is a buffer, which contains appreciable amounts of both the weak acid and its conjugate base. That is not the same as a solution of a weak acid, which, sure, has a little bit of the conjugate base there, but only a tiny amount. This is one you use when you've got basically the same amounts of each. And this is the classic mistake that people make. And to be honest, now, because I run the paper, I can make this decision. And I no longer mark the acid-base questions in the final exam for 191 because it's just too depressing. Because we will ask a buffer question or we'll ask calculating the pH of a weak acid, and everyone just immediately writes this down because they remember that. It's a big formula. It must be important. We'll remember that. We write that down. And then they'll spend like the next 3 pages inventing values to put into this equation, which they don't have because shouldn't, because we never gave them, because it's the wrong formula, right? This is for a buffer. And so it looks like this. the pH of the buffer solution equals the pKa of the weak acid that your buffer is made of, plus the log of the concentration of the conjugate base form of your buffer, whatever the buffer is made of, the conjugate base form, over the concentration of the weak acid form. Right? So the pH equals the pKa plus the log of the concentration of the conjugate base over the concentration of the weak acid. You can also write it this as the pH is equal to the pKa plus the log of the amount of conjugate base over the amount of weak acid. Both are the same, and both will give you the same answer, right? But what you're going to find is that the second one is actually the more useful one. Ones with concentrations are typically what you see in books, but the amount one is oftentimes a better one, because in order to work out what these concentrations are, normally you have to work out the amounts first. And if you can use the amounts, then why do more math to change them to concentrations if you're going to get the same answer anyway? Right? So I would remember this bottom one because it's probably going to be more useful to you. Right? But we need to know the Henderson-Hasselbalch equation. What the Henderson-Hasselbalch equation tells you is that if you want to know what the pH of your buffer solution is, then you just have to know what the concentrations of the weak acid and the conjugate base are in the buffer solution. Right? You know, you can get those. You need to know the pKa of the weak acid, but you can look that up, right, in a book. Or we'll give it to you, but you can look it up. So you just need to know those concentrations. And then it says, note that in using the Henderson-Hasselbalch equation, it's sometimes better to use concentrations, while other times it's easier to use amounts. I like amounts better. And that might just be because I'm a math phobe, but nonetheless, there's some of the stuff in the calculations that we're going to do that just doesn't seem right to me to use when we're using concentrations. So I would always use amounts.